I'll make sure we're on. I'll silence mine over there. And then you will, oh gosh, I always forget this part.
Morning. Oh, good afternoon. Good afternoon. Close. Hmm. I've got a question for you, though. Very important one. What color are these pants?
Yeah. No?
Yeah, they're blue. Will you sign that someplace? Karen keeps on telling me they're dark blue.
No.
Right?
Very much so. Maybe the color faded a little bit.
I think they're black.
Yeah.
We're in agreement.
Okay, because when Terry, I trust Terry, so if Terry said something, I have to question myself now.
I don't. I just go for it.
Oh,
Okay.
wait, before I share, I need to ensure that you are, presentation. Okay, and then I'm gonna test it. I don't know what Brittany will be. She knows the system, but she'll get you there. Here.
I actually have done this, but
Yeah, I mean, it is because I do it a lot, so it got ingrained in share. All right, so you should be good to go. I'll move this out of your way. Okay.
you could twist us.
Okay.
That's okay.
It's not doing that. Oh well. Come in. You know, it's not showing you anyway.
It's okay.
Well, for the people that watches the lecture, you're the important. It's okay. You don't need that part anyway, right? Okay, that's what you need. Oh no, somebody took it.
Yeah,
Somebody took them.
I went through my pockets too. It wasn't me.
I bet it's George. Oh, that's sad. You don't have a pointer. Somebody took it.
Pointer.
Maybe the person that it belonged to, you know. It's good. I was trying
Might
to
have
hide the
retrieved
tears from them. Sneaky. All right, I'll let you start, but I just want to make a quick announcement. We have an FSM club meeting today at 5. So there are these, what do you call them, flyers across the building. So it's an info session. They're gonna be pizza. So come eat pizza for free. They're gonna be fun trivia. But you will learn a little bit more about the club, why it's great for you to be part of it, and all of that. Fun. Please come. Okay, I'll be there if that matters. Okay, maybe they won't come now because I'm.
Okay. Well, last time we finished up gas chromatography, and we're going to move on to mass spectrometry. So it's just another another instrument, and they actually tack these two instruments together, gas chromatography and mass spectrometry. And that's probably one of the most powerful combinations we have. So we'll kind of get into that today. This kind of a listing of a very small number of the applications of mass spectrometry. It's an extremely useful tool. Detect and identify the use of steroids in athletes. Okay. Monitor the breath of patients by anesthesiologists during surgery. Okay. So if you're a doctor, you see someone wheeling up a mass spectrometer next to you, you know, okay. What its purpose is. Determine the composition of molecules found in space. Determine whether honey is adulterated with corn syrup. Locate oil deposits. Monitor fermentation. Detect dioxins or toxins, contaminated fish. Determine gene damage, environment, elemental composition, semiconductors. Determine horses have been doctored for races and so on. And so, of course, people too, any kind of drug dosing and so on. It kind of a diverse application, isn't it? I picked that on purpose, obviously. And so it is, like I say, a very, very common tool throughout the analytical field. Today we'll talk mainly about hardware. What are the parts? What do those parts do? I always like to have some idea of how something works. If I'm going to use that tool, and so to me, that hardware, how it's hooked together is important to me. So anyway, that's what you get for the first lecture. The second lecture, you'll get continuation hardware, but then applications. So show how some of these samples are run, how kind of instruments, what kind of data that you get. So principle of operation, what is this instrument? What happens in that instrument? And we start off with the source. And what's the source? The source is the source of the ions, the source of the energy that breaks molecules down so you can look at the pieces, because that's basically what you're going to do. You're going to put molecules in there one way or another, some material. You're going to bombard them with energy, blow them to bits. And then you're going to look at those pieces that blew into and put the pieces together. Say, these pieces can only come from this material. And so it's very important, obvious part of the instruments. There's different ways that we can blow molecules apart, different ways to put energy into the system. And we'll mention some of those or look at some of those. They generate, of course, neutral, positive, negatively charged ions, but generally we don't give any attention to the negative or the neutral ions. We basically look for positive ions. So, of course, when you blow in pieces, you get different charges, some not charged. But we only collect and analyze the positive fragments that a molecule gets blown into. So there's the source. There is a mass analyzer. So you got this whole bunch of bits and pieces of molecules. Then you start saying, okay, how do I separate them? So now I can count them. I can see what these are. What's the molecule, the fragment, how many parts of it are there? And so that's where the mass analyzer comes in. It takes that whole mess and starts putting it in some kind of order for measurement. Then the detector does the measuring. So basically, it looks at all of those pieces, counts the pieces, and puts them together in some kind of a structure, molecular structure. These are, we got many different configurations, as you'll see. This is one configuration. It's just a good model to take a look at. So we'll see, like I say, different ways to do this. But here we have the various parts of the instrument. We're going to be over here. So this is where we start to show. And so it's this gas source up there. Okay. Then we end up putting our compound in the system up here. Electron collector. So actually gets blown into pieces. It's accelerated down here. And the old system used to be put a magnet up here. And so there's a kind of right-hand thumb rule, something like this, that a charged particle moving through a magnetic field will bend so much. And it bends so much depending on its mass. And so what we're doing is going ahead, generating bits and pieces out there, dragging them out, throwing them up in here. Then we change the magnetic field up there. So initially only certain molecular weight will get over here, get counted. Then we scan that, we change that. So we just kind of go and scan magnetic field, change magnetic field in this case to target our bits and pieces for counting. So that's kind of the principle that all mass spectrometers work on, those particular parts. And that is called an electron impact, EIMS, electron impact mass spectrometry. We're basically, like I say, monitoring or breaking up your compound coming in by an electron beam. So that's where energy comes from, electron beam, bumps it into pieces. Like I say, the pieces get counted and put back together. And the detector down here is really one of the things that make this instrument really a useful instrument, in that we'll put a little detail into this. But that detector detects ions, and basically, so there's an ion multiplier. So whatever comes through gets multiplied many fold. So you might have a little bit of material over here, a few pieces, but when it comes down here, what you're counting gets magnified or multiplied many times over. So that gives us basically a tremendous amount of sensitivity to the instrument. We have to have, of course, the idea that over here we're blowing a molecule into bits and pieces. So we got lots of bits and pieces. Well, let's kind of select what we kind of send down here. Say that, I think I said. We need to drag them out. So we put a negative charge that drags out and gives them that velocity to get up to the separation point. And so this is kind of the overview of mass spectrometry, this electron impact methodology. There's different ways that you can get sample into this system. I guess I didn't show any way of getting it in back here, but okay, we can get different molecules in here, different analytes into that system to get counted. And one way is just putting what you call a direct probe. You basically have the ability, or you put your sample, whatever kind of sample it is, in a little glass tube that goes on the end of a longer tube, and you simply put it into the source bombards it, and away it goes. So you can just do it in that manner. And so a very simple direct probe methodology. We don't tend to use that very often, but if maybe we're collecting some unknown from some other source, we want to purify it, we want to make sure that we get this material in to look at, that's where it happens. So maybe you're looking for something in the ocean, seawater, okay. You need to collect it, and you have to then go ahead and get them sample of water into the system. For gas chromatography, that's a very common combination. I think we probably have 5, 6, 7 of these somewhere throughout our ability, this type of mass spectrometer. And so in this case, I'm worried about flavor compounds, off flavor compounds, good flavor compounds, whatever. And so how do I feed my mass spectrometer? I feed it via the gas chromatograph. So again, you make your sample injection into a gas chromatograph. It goes through this column and separates your compounds, hopefully one by one. They come out. Where do they go? They go directly into that electron impact. So blow every bit of the thing that comes out of my GC column gets blown to pieces, and I look at the pieces. And so a seemingly simple of a process. The other instrument that is really most commonly attached to is a liquid chromatograph. So gas chromatography came first, gas chromatography, mass spectrometry. HPLC has been much more recent. It's fairly convenient if you think about it. For a gas chromatograph, I have my compounds that are already in a gas phase. They're already moving along their merry way. So, okay, you just dump it into the mass spectrometer. You look at an LC, what's it in? It's in an organic solvent of some kind, or I suppose aqueous solvent, but your sample is in a liquid. You're not going to be dumping liquid into the source. That wouldn't work very well for you, because all that liquid would get counted too. It would get in there in fragments. So It's much more of a challenge in HPLC to get your sample into the system. For gas chromatography, like I say, it's a really simple combination. We actually hit each of these compounds that are coming out of a gas chromatograph, hit them with 70 electron volts, and that blows them into bits. Actually, the molecule simply explodes. Chemical bonds are about 10 electron volts, and you put them way over what it takes to break them. So you literally do blow it into pieces. The more pieces, to some extent, the more bits of knowledge you have to put things together. And so that's helpful to us to blow it up for the most part. And I'll give you a situation later on where we don't want to blow it apart, and we use a much lower voltage. So we may take intact molecules, but that's less common. So like I say, we nail them with about 70 electron volts, blow them into pieces and start them down their merry way. This is again two different voltages or energy levels, I could say, that we use. The like I said, high energy blows everything to pieces, and so that gives me lots of pieces to put together. Very helpful. Disadvantage: we like to see what we call the parent ion. We like to see the compound, the mass of that compound, go through intact. So we want some of that parent present. And so, yeah, with a high energy electron source, that molecule just may blow into pieces. We won't see the intact whole molecule. And why do we want to see the intact whole molecule? Because for quantitation, you're going to be looking at measuring how much of something is there. It's kind of nice to have that one peak. That's our molecule. If we blow it into 70 pieces, then they got to add up the 70 pieces or 100 pieces, put them all together and come up with a number and quantitation. So the high energy is a disadvantage. We may not see the parent, and that means we may not get good quantitative data or as good quantitative data from it. So we both have combinations, a high energy system and a low energy system. So low energy, that's not 70 electrons volts anymore, it's much lower. And so at that point, we will bombard our compounds coming into the system, and they may just pick up a couple charges, few charges, and go on their merry way. They won't be blown to bits. And so the mass spectrometer then measures those ions and determines its mass and says, oh, that's a mass of 172. Good, we'll quantify our compounds that way. So we want to use it for quantitation, we'll probably use low energy. If we want to do identity, we'll probably use high energy for that purpose. It's just in some terms that we'll use, the positive ion of the unfragmented molecule is called the parent ion. That's just what I was explaining. The parent, it's the intact molecule just with a charge. Another term that we use in identification is the base peak or the base ion. And that's the most abundant fragment. So it blows into a lot of pieces. We tend to be interested in what's the most abundant fragment in our system. Again, helps us in identification. And so, and quantification for that matter. So those are terms I'll use, and hopefully that helps in terms of identification. This is an example of a mass spectrum. It's a chloroacetylphenone. I wouldn't say it's a common component in foods, but this is just simply a good example. Since we've lost our pointer, your pointer, so hopefully you'll have some idea where I'm pointing at. So this is kind of what that molecule is up there. There's two benzene rings. There's a chlorine on one end. There's a carbonyl C double bond O in the center. And so when this takes on this energy, it gets blown into fragments. And those fragments then are presented up here. So that's our intact molecule. That's our parent ion. There's a mass of 216. They have mu. So it gets blown into pieces. What kinds of pieces do I get? Well, we actually get some pure benzene rings. So if I kind of look at the molecular weight and how much of something's there, okay, we've got our aromatic ring at 77, should be 78, it's lost one, so it's charged. And we have 105, so you can see where it broke, so that we get the C double bond O attached to that benzene ring. We'll also get this bottom piece broken off here, the aromatic ring with chlorine, I almost like chlorophyll. And then we've got another piece up here. So if we look at the spectrum of this, it's primarily 1, 2, 3, 4, 5 peaks that we would find in there. There will be more because the benzene ring gets blown into pieces and some other things happen, but sort of the major pieces. And how is it displayed? It's displayed as we go along here. So you'll get a chart. You'll love this. I've been around a while. It was my job at Penn State to run this instrument, this mass spectrometer for the service for the department as a whole. And so I've had a good deal of experience with this. And of course, if you think enough years ago, it wasn't quite as sophisticated as today. So we get everything nice and computerized and whatever. It actually spit out on a roll of paper. It was UV sensitive paper because it had to go fast and UV light was burning images. And so you push the button and it would spit out about 6 feet of paper. And you'd sit down and with a measuring, you'd sit down on the floor and kind of measure, okay, that peak's that high. Oh, that's that high. Oh, that looks like that. So if you ever get disappointed or frustrated in working with a mass spectrometer, I want to tell you that it could be worse. It has been worse. It's like everything else, just the innovation, the development of the ability to measure things. And so it's absolutely fantastic. I love it. So anyway, that gives an example of what is apparent ion, and you'll get that spectrum. Of course, as things have progressed, we've accumulated tremendous libraries of compounds and so computer power, so that the computer power can take this and feed it in and say, I get this much of this peak, that much of that peak of that mass, I suppose I should say, and then start searching, the complete library of all compounds ever been identified, and it'll make a match for you. And so you don't have to mess around with it. Basically, the instrument does the identification work for you. I said we can use low energy ionization, or we can use this high energy, so 20 electron volts or 70. And this is the difference between a 20 electron volt mass spectrum and a 70 electron volt mass spectrum. I was going to say there should be a little more difference, but that's not bad. If you use only 20 electron volts, it breaks only the weakest bonds in that molecule. And so what do we find? We find basically our mass of 228 is out here, is a tiny piece, and then the bigger mass is 227. So that's a molecular weight loss with the loss of a hydrogen. So we've got a few peaks, few mass fragments to work with, ranging 157 to 227, so mainly out in that region. As we go to the 70 electron volts, we of course blow it into smaller pieces. So low energy, we get a spectrum like this. High energy, we get a spectrum like that. So your spectrum depends upon the energy that you put into the system. Now there's different ways we can ionize the molecules. And so these are some examples, and we'll probably go through these as well. We have a really good MS center on the Minneapolis campus, a pretty decent center on St. Paul. And actually the Minneapolis campus is moving all of their facilities here. So we'll actually have a nice MS system, analytical service on this campus very soon. And so they do have basically all of these techniques in the MS system, or service, I should say. If you look at what we've got, we meaning the department collectively, we have only really one type for gas chromatography, and that's the system I was just showing you. So we don't have these other techniques for ionization, and each of them bring a certain strength, a certain bit of information to you. So it isn't like you have only one detector ionization system. You'll have very many different types if you're going to be looking at different compounds. When you get to LCMS, and I don't tend to go there often, I like gas chromatography. Bram would be happier with LCMS because she works with big molecules. For my gas chromatography, I work with things I can make gas. She can't do that to proteins and other, lipids or whatever she happens to be interested in. And so she will be much happier, is much happier using the ESI, electrospray ionization. Like I said, we'll cover each of these very, very briefly. But the most commonly is electron impact for gas chromatography. The most common for liquid chromatography is ESI, electrospray atomization or ionization. We'll go through these in just a bit. So MALDI matrix assisted laser desorption ionization. We use that. Actually, I do in some cases because I guess I do have an interest in proteins. So, okay, I'll change my story a little bit. I do work with electron or matrix assisted laser desorption, MALDI. Application: high molecular weight analytes. For example, analysis of proteins, peptides, glycoproteins, oligosaccharides, oligonucleotides. They're not particularly high molecular weight proteins. I work with beta-lactoglobulin a lot. I'm interested in how flavor chemicals react with proteins. I'm interested in it primarily because of nutrition. So we put a flavor into a system, or we have some other source of chemicals. And like I say, my interest is flavor reacting with protein. The flavor will chemically bond to that protein. Think of the amine group out there that's hanging off a protein, off lysine. You think about the carboxylic acids, the alcohols, a lot of functional groups on proteins. Well, my flavors are also a lot of functional groups, and they will chemically bond, and my flavor goes away, or some part of my flavor goes away. And so I am really interested in looking at proteins and how flavor compounds bind to it. So I certainly am interested in this. I guess as the example up there of a lysine side chain, there goes my flavor. Last night I was on a panel at Purus. Was anybody there last night from here? No. Well, Purus had. Do you know who Purus is? I mean, they're basically protein people. Okay. They hosted the Research Chefs Association, and a few people, 3 people, were invited to be, I was going to say guinea pigs, but the people who sit in front and answer questions. And I was one of those people. And what they were doing is they were showing their proteins in hamburgers. And, the idea, you've got your little burger on a bun, and the Research Chefs people, they actually made 3 different kinds of burgers on a bun. And I was actually quite impressed with them in terms of the flavor quality. They were really, really quite decent. They lacked meat flavor. It didn't, plant protein didn't turn into roast beef simply by heating it. But it was really quite, what I say, clean, pretty bland. So they, the chefs had to add all kinds of nice things and sauces around them. But, of course, the first thing I do is take the burger out, scrape it off and say, no, I want to taste that. What's that taste with? And it wasn't offensive, but it wasn't beef. It was just kind of nothing there. So, and I think nothing's probably better than something bad, but it wasn't, you'd like to go on the merry way. And, but it was really an interesting meeting, and looking, my concern is down here, if they start flavoring that, they start putting flavors from a flavor company into it, and then the consumer fries it, boils it, whatever, they're going to be forcing chemical reactions between the flavor and the protein. And guess what? That flavor that the flavor company just sent you isn't going to be quite right because pieces of it have been reacted with the protein they're flavoring. So it's not a simple one. So how do we do this MALDI preparation, MALDI mass spectrometry? Samples pre-mixed with a high energy absorbing matrix compound. Matrix assisted, they put your analyte into this matrix that's going to help it attract ions and basically blow to bits. And the matrix transforms the energy, laser energy, into energy, and basically that will get transferred. Some of the energy will get transferred to what you want to measure, what I want to measure. And it isn't a high energy system. And so we get mainly the parent ion. What I showed you before, we're blowing that compound into pieces. With matrix assisted systems, you basically have very, very little energy that's transferred. So it really doesn't blow into pieces. So you get a nice picture of a molecular weight. So I can look at the molecular weight of what I want to look at, and for me, that's a protein. This is an image of kind of how that works. You've got your purple up there, which is your matrix, and you have your components of interest in there. So you'd actually go ahead and stir up your protein if you would want it with that matrix, bombard it with a laser, and your ions then will be kind of forced out under high voltage and forced down to a detector eventually. So they're focused and get down to the detector. And so there's little fragmentation. And so that makes life easier in terms of sensitivity. If you blow it into a lot of little pieces, you got to count this, and this, and they're all fairly low. If you don't blow it into pieces, you got one ion in there, and it's much easier to count, quantify, or much more sensitive. And so we're basically looking at little fragmentation, which really gives good sensitivity. Where I run into problems is that, okay, I'm going to actually hit this protein with a fairly low energy. I'm going to put only a few charges on. I really want it to go through the gas phase and go around the circle. If it's too big, it's not going to happen. And so it has a mass limit. And actually, that's why I work mainly with beta-lactoglobulin. There's a mass around 18,000. I can see a compound of 18,000 molecular weight really well. If you want to get into larger proteins, forget it. I won't see anything. They won't be ionized. They won't get carried along through the process. So the MALDI, or matrix-assisted laser ionization, does have a molecular weight limit to it. And that can be a problem that depends upon what you're looking at or want to look at. It is called soft ionization. It doesn't blow into bits, just kind of drops on the charge. Wouldn't you like this charge? Here we go. And it goes on its way. This is an example, and this is actually a fairly small molecule. It's, well, I guess it's not so small. There's some bits and pieces that happen over there. We're not really interested in this. But this one here, what is it? It's a mass of 2,466. And so this would be an example of this particular compound. Not fragmented at all, except there's a little bit down there, but it's basically one compound. And as I said, my interest tends to be in a much larger molecule. And that's 18,000. So that's what we're seeing. Kind of at the peak up there, 18,337. So there will be a blip. There'll be a corner if it's added on. If my flavor compound gets added on there, it'll go up for the on label or on reacted and give me, okay, here's another fragment, another piece. So it's fairly simple. I get one mass spectrum for the protein, and then typically one higher peak for one is added on flavor compound. And this is just another example, 18,622 mass. Here's our protein next to it, and we've got added flavor compound. So to me, it's really, really simple. I want to know if my protein is reacted with my flavor. I can do it by mass spectrometry, and I'll see what's added on to the protein. It's a nice nice test. This is, yeah, adding on vanillin or vanilla to the peak. So we're not looking for much blowing into pieces. We want to have just a mass so we can say what's added on, how much molecular weight. Fast atom bombardment is again where we actually ionize the molecule, and we will do that by blowing it into more pieces though. So it's a higher energy, kind of work our way up. And so we'll get more fragments out of this, which means we get a little more information on what's happened. I'm only interested how much is there and how much isn't. Okay, but you may be interested in what other things. So several components perhaps. And this uses a slightly different system, glycerol, 3-nitrobenzene alcohol. That's your matrix. You put your sample into the matrix, and you bombard it with argon or xenon, energies of 4 to 10 kilo electrovolts. So just another means of ionization, a little stronger. And what that tends to do, and maybe we'll see that, if you get multiple charges on an atom, I can move it along a field easier. My compound, my protein has 1 charge. This will put on maybe 20 charges onto that protein. And so it's easier to drag it out. It's easier to put it around a corner and measure what's there. And so that gives us a larger mass range for one thing. You can do much larger proteins in analysis. And this is very similar to MALDI. And so you put your analytes on a little platter. So what do you want to analyze? You put that into a matrix that will transfer the energy. You'll bombard it with high energy. That's the red droplets coming down. So high energy, bombarding that matrix and producing all kinds of ions that you can then drag out and get much better sensitivity. So there's blue up there are charged plates that are going to be dragging these ions up, and where they'll get counted up above. So a lot better sensitive. DESI, direct electrospray ionization. In this case, you put your sample out, and you can then bombard your sample. It's just pure sample. There's nothing else to it. Pure sample. It gets bombarded, blows some things up, gives them electrical charge, and we just kind of bounce like that, and we collect ions up there. Have you ever been to an airport? I expect most of you have. Have you ever been checked by the people and say, take a little swab and put it in the mass spectrometer to see whether or not you're carrying anything along with you maybe shouldn't? That's done mass spectrometry. It's a very, very simple, very quick, simple, quick process. Either use the system just before or some version of this. Very quick, sensitive methodology. And the mass spectrometer doesn't tell you there's something there, it tells you by fragments what is there. So they know what you're looking for in terms of a bomb. And this is kind of showing the convenience of this, where you've got your ionizing material coming in here, your energy coming here, bouncing it off the surface of the tomato, and then we've got a little tube over there connecting the ions. So, hey, I want to see if there's pesticide, residual pesticide on this tomato or herbicide or whatever. They can literally take the tomato, bring it to the mass spectrometer, bounce it off the surface, and detect whether you've got residue of pesticides, herbicides, and so on. So it's a really fast, convenient, and it's really quite sensitive. It comes right down to it. It's very, very sensitive. This is again a different system, but it's very, very similar. Also used for looking for things that should be there, explosives, and you name it. Again, airport say kind of application could also be used for this. So it's just a little different system of ionizing the surface of a material and looking for what fragments occur and what charges occur. In these later systems, their molecules may have more than one charge. You know, for gas chromatography, we like to see one charge per fragments that blows into pieces. I want that material to have one charge because I'm going to be measuring charges. If I want to quantify how much of something's there, if you got many fragments and different amounts on each fragment, it's hard to put them together, know what you got. And so this gives you an opportunity to actually have the mass spectrometer start working to kind of put those charges and masses together. If you've got a molecule that says a certain mass and you add one pesticide, okay. But maybe you add two pesticide molecules or fragments from pesticide molecules, but the instrument knows if it's got one and two, it's built up that big. Okay, this is together, right? These two materials, if that makes sense or not. But you do actually permitted to look at fragments and add those fragments because the machine knows it came from the same source. And so the idea of working at high mass, 20,000 AMUs is really pretty easy. You get into more trouble when we start getting into larger molecules, but up to 20,000 is a really pretty simple methodology. So those are different ways of making ions, breaking compounds down, putting in charge. Then we have, like I say, the task of measuring what was just formed. And these are different, what we call mass analyzers. So we blow this thing into bits and pieces. How do we separate those bits and pieces so we can count them and see how many they are? Historically, it was a magnetic sector. There's a right-hand thumb rule someplace that says about an ion moving through a magnetic field is a certain force. So it's actually bent around. Again, the first instrument I worked on was a magnetic sector. You didn't get close to it with any metal, just because the magnetic field was so strong. It'll take things out of your pockets. So anyway, magnetic sectors were the oldest methodology, and they still are used in some places. There's just easier ways to do it today. And so the quadrupole is by far the much more common methodology, and I'll kind of go through the quadrupole, ion trap, time of flight. So let's go ahead and do that. Here's our magnetic sector. So we get our ions formed over here. We will put an electric charge to dry those ions out. So the ions will be coming towards the electric charge. So could be going this way and they'll be focused down here. As they get down here, we've got a magnetic field, and we can change the magnetic field. So it's electromagnetic, make it very weak. If it's very weak, it won't bend many ions around. It'll only bend the smallest molecules around. Put a little more magnetic charge, we start focusing higher masses and higher masses and higher masses. And so this would start counting on the very small molecules. Okay, got about that much small molecules. Change the magnetic field. Oh, I got bigger molecules bent around the corner. And it will give me a plot, literally, of the ions that this molecule broke into. So it is the first system. It's actually quite convenient. But they're big, they're heavy, they're inflexible in many ways. And so we've really left them behind. There's just better ways to separate ions than magnetic fields are. This is a time of flight, and this has become probably one of the more common detectors of the fragments that a molecule gets blown into. And in this case, what you do is you blow it into pieces. So we're going to take a laser beam. We're going to go ahead and aim that laser beam at our analyte of interest. It's going to break these ions into pieces. We basically look at how long, and then there's another magnet up there. So we're going to be drawing ionized pieces up this tube and focusing them. So what we do is the machine times, it goes a zap, and then look at the electric field, changing the field. How long does it take to pass from here to here? So it's times it. The more charges, the faster it goes. And so it's really a convenient, accurate methodology for measuring ions and getting them detected. I say that's probably the most common detector today. The cheaper way to do is with what you call a quadrupole, and I think that's probably what we have most of in the department. And so, as far as I'm concerned, that's magic. I don't quite understand it. I know what gets accomplished, but I have no appreciation for the mathematics that gets you there. And so, in that case, you go ahead and take your analyte, you zap it so it's got electric charge, and then you put another charge on the other end. So it's drawing these charged molecules out between these four posts, and these four bars. And those bars have set up with electric fields. So they will actually focus at one setting, very low molecular weight molecules with little charge. They'll go up there, then they change, they kind of scan through an area, so bigger and bigger molecules get focused to come through these poles. And so it's say very simple. It shows kind of a diagram up here. If you don't have the second one down, so you don't have the right combination of charge on those poles. If your ion of interest comes in, goes, well, hits the pole, disappears. If you do it right, you're up at the top. Okay, so those poles are changing constantly in terms of the strength and direction. So they go through this pattern. And so you get up at the top, okay, that mass at 100 under certain conditions makes it to the end. So it's a nice way. Basically, you just focus the path of ions to make it through those poles and end up being detected. So it's a cheaper way to do it than many of the other approaches, and like I say, works really quite well. The ion trap, I count this one as magic, and so meaning I don't have the faintest idea how the heck they manage this, but in this case, in an ion trap, what they do is you blow the molecule into pieces. Those pieces, and electrical charge and so on, get put into a trap. And then that trap is set up with electromagnetic fields that it just kind of keeps everything, like a crystal ball kind of hanging out, but they then key it. So, okay, this mass will make it out, and they count that. Okay, then we'll change it again. This mass will make it out, and they count it. So it's trapping all the ions and then setting up their release so they can be measured. They've been around. They're not quite as good as the quadrupole, so they really haven't found the use that the quadrupoles do. What makes this detector so good, or contributes to making it so darn good, is that you're detecting charged molecules. Gas chromatography, you probably don't have charged molecules, but in mass spectrometry, you do have them. They all have picked up an electric charge. That's how we got them down the pathway to the detector. And so we kind of look over here. So here's kind of this little stream of bits and fragments coming in with a charge. And they actually then go on a pathway to that electrically charged plate there. So one electron hits that plate and maybe gives up 2, 5, or 10 electrons. Okay, but that's also then focused. So those 2, 5, 10, whatever, go down here to make 50, 100, 1,000, 10,000. And so it's called an electron multiplier. And so it basically takes whatever signal you got and makes it big enough to measure. So we've kind of got a best of all possible worlds when we kind of look at how these system works. So you don't have a lot of material, and we take care of that through sensitivity by simply multiplying these charges. So that charge just makes it really simple to do. So how do we go ahead and do these interpretation? What do you do with this? It's You don't see that very often anymore, but that basically shows the amount of like ions of different molecular weights. And so that's kind of the pattern you get, or the machine computer gets. It gets a pattern. And then it has to, like I say, search its libraries to find a matching pattern for that. The matching pattern, of course, then gives you an identification. This molecule gives a pattern that looks like this. And so it's progressed to make life easier. Again, I think that's common in most cases, is how do we make this easier, more available to everyone? Back again in the old days, you'd get that and you'd try to work with it and try to figure what the heck it is based on that. Now, again, the computer takes that pattern and says what fits. And like I say, the spectrum libraries are available. PubMed is what we tend to use most. They just all have nice spectra available for you and other information. So the machine tells us what it is, so we actually don't even bother to go to PubMed. We let it tell us what it is, and we trust it. How's that most of the time? High resolution. Okay. So everything I've been talking about in terms of detecting ions has been somewhat crude. Crude in the sense that it's not good at detecting tiny differences in charge. And so that means that it's a little harder to get elemental formulas. You may get a formula, but elemental composition, what's there. And so we have detectors that'll give much better resolution. Most of the time, like I say, our instruments, where resolution is one mass, it's either this mass plus or minus, 0.5. And so we'll go. But when we go to a high resolution, it does a mass to 3 or 4 decimal places. If it goes to 3 or 4 decimal places, an elemental composition. It can only be made up of carbon, this, and this in this proportion. My mass, if I give a mass in unit resolution, there might be 20 compounds, 30 compounds that fit, a low resolution spectrum. This says no, it can only have this elemental composition. Doesn't necessarily tell you how it's put together, but it gives you an elemental composition. And so high resolution instruments, we don't have any down in our building. Again, if we want high resolution, we'd have to go up to the MS Center and do that. Why don't we have one? They're expensive, they're fussy. You'd rather let somebody else worry about them. You come and use them from them. So our units are all low resolution, or call it moderate, sounds better than low, moderate resolution, and not in this category. But the nice thing about this, like I say, is it gives you elemental composition. It can only be this combination of molecules. And the idea of computer searching, every one of your instruments will have a nice computer attached to it, and every one will do the math for you, and they'll come up with the identification. But that doesn't mean it's necessarily correct. So how's that after all we've been going through? If it's a little bit weak, there's not a lot of compound, you don't get a good spectrum of it, it's a little maybe high molecular weight, okay. You're not going to get a match. And so computers today now are set up so they give you a probability of a match. So when you go through this whole process, it'll give you an identity and it'll say, I got a 60% confidence this is correct, 99% confidence this is correct. So it does matches for you, and it tells you how good its guess is. And that's really, really helpful, because again, sometimes compounds are very similar, they're very close, and it's tougher to make that decision. But the instrument does a nice job of now adding that level of uncertainty or certainty into the system. And that's where, again, it helps if you know what you're doing, you know what you expect. And so people don't get out of this. You can't simply pass off as a machine said. I'm having fun.
You want to finish your thought?
Yeah, you guys can go. Okay. I guess I have to quit. I can stop.
Yes.
Not, that wasn't long ago, right? Okay. Okay. We're on slide 37 of 77.